is Anjali Krishna, and I am a rising sophomore at River Hill High School. I am also part of the Howard County chapter of the KCS Youth Club.
Hey everyone, my name is Anu and I'm a rising junior at Northwest High School. I am a part of the Montgomery County chapter of KCS Youth Club. As Pranav mentioned, our speaker today is Dr. Rajat Varma. I'll be introducing him tonight. Dr. Varma is a drug hunter developing immunotherapies for cancer at AstraZeneca. His scientific journey began as a master's student in physics at the University of Pune. Inspired by his high school biology teacher, he decided to enroll in a PhD program in cell biology at the National Center for Biological Sciences in Bangalore. During his PhD, he became interested in how the body mounts immune responses and how immune cells move and search for pathogens. To pursue this, he came for his postdoctoral studies at the NYU School of Medicine. Here, he pioneered the use of a microscopy technique called total internal reflection fluorescence microscopy to visualize how proteins on the surface of immune cells organize themselves to transmit signals that allow them to discriminate self from pathogens. In 2008, he was recruited to the National Institute for Allergy and Infectious Diseases as a tenured track investigator. Here, he continued to study how signaling events in immune cells coordinate immune responses. In 2016, he decided he wants to contribute to human health through the development of therapies for cancer and autoimmune diseases. He worked for several companies before joining AstraZeneca in 2021, where he is Director for Oncology Research. Welcome, Dr. Varma. We are so excited to have you speak for us today.
Well, thank you so much for that very kind introduction, Nu. And also thank you for inviting me and giving me an opportunity to speak to you all. Today, I'm not going to talk a whole lot about biology. I'm going to talk about first a little bit about physics and then and mostly about light and how understanding the properties of light over the last 300 to 400 years allowed us to develop some rather cool techniques to visualize how biological systems are organized and how biological processes are coordinated. So I like this seminar to be interactive. So at any time you think that I'm saying something that doesn't make any sense, please raise your hands and ask me a question. The more questions you ask, the more you will get out of this webinar. And I hope to convey a few points, not a whole lot of information. So I have limited my slides to less than 30. Okay, so one of the questions that, has bothered thoughtful people like you for last 400, 500 years is, what is light? And this is one of the first sensations that we encounter. Most species on Earth have eyes. So as you're born, this is one of the first stimuli that reaches your brain. We see light in so many different forms in the stars, from fire, fireflies, and even from man-made light sources such as lasers and so on and so forth. So what is our understanding of light today in the 21st century? So we all agree that light is a form of energy. You can take a lens on a really hot day and focus the rays of the sun onto a piece of paper, and the paper is going to go up in flames in no time. So definitely it carries a lot of energy. It's also called electromagnetic radiation because light is made up of particles called photons. And light has an electrical and a magnetic component. And this is sort of described over here, where you see electrical vectors when they are rising down. orthogonal to those electric vectors are magnetic vectors that are rising up. So if you remember from your high school physics that electricity and magnetism are very intermittently linked with each other, and that linkage holds true in light as well. And we all know that light travels in a straight line unless, of course, it encounters a piece of glass or it encounters water, then the light can bend. The other thing we know about light is that its speed is constant in vacuum. And that is something which was quite the discovery, that you cannot expect light to travel at different speeds at different times. And then the other important piece of information was the description of what's the energy in a single photon. So the energy in a single photon is related to something called a Planck's constant, which we'll come to in a bit. And it's related to the speed of light and the wavelength of the light. So as you know, that light it has many different wavelengths. What we see by our eyes, the visible spectrum, light comes in forms that our eyes cannot see. Namely, it can be X-rays or gamma rays or ultraviolet, or you can have infrared and radio waves. All of these are forms of light. Here are examples of two different photons, one with a longer wavelength and the other with a shorter wavelength. So from these formula, you can imagine that a photon that has a very long wavelength would be of lesser energy, and photons with shorter wavelength will carry more energy. So consequently, X-rays and ultraviolet are photons that are very high energy photons. And likewise, infrared are low energy photons. So that's the reason why when you go to a doctor to get an X-ray done, they always protect areas of your body that are not to be imaged, because you want to limit the amount of radiation that your body faces. And the doctor himself will set you up, go outside the room, switch on light, switch it off, and your X-ray is done. So the X-rays are powerful photons that penetrate your body and allow the doctor to make images of your bones and other tissues in body. So the discussion around the nature of light began 300 to 400 years ago, and there were two competing theories, one put forward by Sir Isaac Newton, who essentially hypothesized that light is made up of particles. And then you had Christian Huygens, who basically observed different other phenomena of light and basically said, no, light cannot be a particle, it's actually a wave. And Newton came up with this theory that light is a particle based on the observations that, light travels in a straight line. So it's like a stream of high energy particles. If they have very high energy, then there's nothing that's going to impede their motion. And then he was also looking at phenomena like image formation by lenses. But his explanation was for why light bends in glass was counterintuitive to what we know today. He actually thought that once light enters glass, it actually increases its speed because it would interact with the dense material of the glass and absorb energy from the glass and thereby travel faster. At that time, there were other different phenomena of light that were known. One, of course, is that light would reflect from surfaces. We all know that you can use mirrors to steer light in any direction you want. You had the phenomena of refraction that I just briefly talked about. And then Newton also described the phenomena of dispersion of light, and I'm going to get to that in a second. And the other two phenomena that were known about light were interference and diffraction, all of which were explained by the wave nature of light. So essentially, the wave nature of light was accepted till about the end of the 19th century. And to explain the propagation of light in vacuum, it was hypothesized that the universe was filled with a substance called ether. And we all know today that there is no such thing. But back then, when people thought of sound propagation, we knew that you could not propagate sound in vacuum. So you needed air, or there was no propagation of waves in water without a water. So essentially a medium, everybody thought that you needed some kind of medium for any kind of wave to propagate. So these are some of the phenomena that I was talking about, that these are the different properties of light. When you think about light, these are things you expect light to do: reflect from plane mirror surfaces. If you take a beam of white light and you put it through a glass prism, it will separate out in all its colors. So all the way from red to violet. And remember this, that red light is low energy, violet is high energy. Light also undergoes something called diffraction, meaning if you take a pinhole and incident a beam of light, this beam of light will essentially start bending at the corners of the pinhole, and this light will start producing an interference pattern on a screen in front of it. And this phenomena is known as diffraction. We know about refraction. When light travels from a medium like air into glass, it will bend, and it bends based on what is called the refractive index of glass with respect to air. And these angles are then sort of nicely predictable by the ratio of the sines of these angles. Light can also undergo interference. You can create two separate slits from a single source of light, and light emitting from these two sources will start interfering and produce an interference pattern. And this is also something that we have seen water waves do. Sound waves also do the same thing. So there were a lot of similarities between what waves on water or sound waves would do, and what light was, what was observed for light, and that was part of the reason why people thought that light is a wave. Then there is another phenomenon that is called total internal reflection. So if you take a beam of light from air to water, it's going to bend towards the perpendicular line at which it is being incident on. But if you do the reverse, if you take the light that is inside the water and it's trying to go out, you will actually see that the light deviates away from the perpendicular angle. So if you now take this incident ray and keep on increasing this angle, at some point what happens is that the light keeps bending away and away from the normal. And let me put our meter. And then it starts traveling on the surface of the glass or water and air. And beyond that angle, which is called a critical angle, this light can undergo total internal reflection. So I don't know how many of you have done this experiment where you take a glass of water and you just drop in a coin. And at a certain angle, you never see the coin. And the reason is that the light rays coming from the coin undergo total internal reflection from the surface of the glass filled with water. So this is the phenomenon known as total internal reflection. So at the turn of the 19th century, Max Planck in Germany was trying to understand why, or understand the nature of light coming from objects that were very, very hot. So as you know, that you can take a piece of metal and put it on coals of fire, or you put it in a furnace. After a few hours, this piece of metal will become very, very hot. And as you can see that the parts of the metal that were in the fire were glowing yellow. Parts of the metal that were slightly away from the fire are glowing red. And parts of the metal that are cooler are probably emitting some light that our eyes cannot see. So the ability of any object to emit light at a given temperature without the input of energy from anywhere else, uh, except what was given to it to raise its temperature, is called a black body. So everything around you, which is at a temperature above zero, by zero I mean not 0 degrees centigrade, but above 0 degree Kelvin. How many of you know about the Kelvin scale? Good. So the Kelvin scale is the scale of temperature which describes temperature from absolute zero. So at 0 degree Kelvin, everything is so cold that you do not even expect any molecular motion. So if you, for example, liquefy helium, the temperature of liquid helium is 4 degrees Kelvin. And so that's like really, really cold. And then room temperature is close to about 300 Kelvin. So we are far away from absolute zero. I don't know how many of you enjoy winters, but as soon as my body starts going towards 0 degrees centigrade, I start to have trouble. But yes, so essentially, even a body that is sitting at room temperature is emitting photons. But those photons are essentially in the far infrared scale. And if you take any body at any temperature and you're able to measure the dispersion, right? And you just measure that at each wavelength, how many photons are coming out. And you do this experiment at different temperatures, you get this plot that looks like a distribution. A distribution is simply this, that let's say that you have a class of 100 students, yeah, and you want to plot how many of your class members like football, how many like cricket, how many like table tennis, how many like tennis, yeah. And out of 100, you ask them, and you basically count them here, and you will start seeing certain graphs. Maybe there are 10 people who like cricket, maybe there are 15 who like football, maybe there are, more than 50 or so that like something else. So you start making a plot which is called a distribution. So here, what we are doing is in this plot is that we are essentially counting how many photons coming out of the object are having wavelength, which is 500 nanometers. How many of them are having wavelength, which is 1 micron? How many of them have that is wavelength that is 1.5 micron, and so on and so forth. So after you've done all that counting, you create a plot which is called a distribution. Okay. And you will encounter distributions of every sort. For example, there are distributions on people traveling by plane over the course of the year, total number of travelers. And you can see that in the summer months and the December months, the number of travelers is going to peak because that's the holiday time. That's when most people travel. So that is a distribution of number of people traveling in every month across the year, from which you can draw inferences like, why are they traveling so much? And why are the ticket prices suddenly so high in December? Oh my God, it's like $2,000 for a ticket to Florida. It's because everybody is trying to escape the cold and go to Florida. So, long story short, at the turn of the 19th century, people started experimentally determining these distributions coming from black body radiators at different temperatures. So this is a black body at 3000 Kelvin. This is a black body at 4000 Kelvin. This is a black body at 5000 Kelvin. And what you immediately notice here is the hotter the object gets, the shorter the wavelengths become. Is that obvious to everyone? Yeah, because the peak of the distribution of the blue is close to 600 nanometers. The peak for the 4000 is close to 750. The peak for 3000 is close to 1 micron. So if you think about, or if you assume that light is a simple wave and try to build a mathematical model of what that distribution should look like, you get this black line. So this bothered Max Planck a lot. And he basically started playing around with some ideas. And one of the ideas that he played around with is he basically made the assumption that photons coming out of a black body are not assuming all energy states, meaning that they have energy that are multiples of a unit of energy. And he called this unit the Planck's constant. And we'll come to that in a second. So he basically said that there must be something in the materials because of which the photons cannot assume any energy they wish. That there were certain constraints, and these constraints led to the birth of modern day quantum mechanics. And then it was Einstein who essentially proved Planck's theory and said that yes, it is true that light can only have a discrete energy states. And he basically said that a unit of light has energy that is a function of the Planck's constant times its frequency. And the frequency is nothing but the velocity of the light divided by the wavelength of the light. And he also described something called a photoelectric effect, which essentially said that if you take any substance and hit it with light, the electrons in that substance will absorb that light, absorb the energy from that light, and will get a certain kinetic energy, which is the difference between the energy state of the electron and the incident light. So if the incident light has the energy h times the frequency, and the state in which the electron is W, then the electron will get a kinetic energy, which is the difference between these two values. And this electron, now that it has become free, can increase the conductivity of that material because now it is free to move around and transfer energy. So these two phenomena really made people think that maybe light is not a wave. Light is indeed a particle. And there were subsequent experiments that essentially proved that indeed, yes, light was a particle, which was then called the photon. Any questions so far? Okay. So Millikan was one of the scientists who thought that Einstein was wrong. He really thought that light was indeed a wave and not a particle. And so he basically developed an experiment, which is the complex apparatus is shown in the left, but a simplified version of that apparatus is shown here on the right. So what was in his apparatus? So in his apparatus, he basically had 3 different metal plates made of 3 different materials. He had a plate made out of sodium, he had a plate made out of potassium, and a plate made out of lithium. And what he did was he basically applied a very high voltage on these plates relative to ground, by ground being 0. So these plates were kept at very, so there would be a certain baseline current that will flow from these plates to ground because of the free electrons that might exist in these plates. And then what he did was he essentially showed single wavelength of light on these plates. And what he found was that as soon as he would shine light on this plate, the current that he was recording would go. And instead of disproving Einstein, he ended up proving Einstein that indeed photons can increase the energy state of electrons. And what was really beautiful here is because he had plates made out of different metals, he could get different kinds of current coming through depending on which plate he used and which wavelength of light he incident on the metals. Because as you know, each metal comes with a unique atomic number. And that atomic number decides how many protons and electrons are there in those atoms. And the electrons in each element have different energy states. And so you would expect that they will absorb light of different wavelengths depending on the energy states that exist. Yeah. So this is one of the fundamental aspects of quantum mechanics, is to understand how electrons and protons are organized in each element and how light interacts with different elements. And what really, then light becomes a probe to understand the electronic states of each metal. So this becomes a fundamental basis of a field called spectroscopy. And from 1900s to 1950, there was a lot of development in atomic and molecular spectroscopy, where you would basically shine light through different substances, different molecules, and you derive information regarding how electrons, protons, and neutrons may be organized in each of those substances. Then it was another scientist called Compton who actually really demonstrated the particle nature of light. What he did was that he essentially took an X-ray, and as I mentioned to you before, that X-rays have very high energy. And he incident the X-ray on a piece of graphite, which, as you know, is made out of carbon. And this X-ray would essentially bounce off the graphite target, go through a slit, go through another crystal, and then be detected on an ionizing chamber here. So what is the graphite doing? Essentially, what he was trying to observe was what happens to the X-ray. So if the X-ray hits a nucleus, it's like a tiny ball bearing hitting a football. Okay. What happens is that nothing much happens to the football, but the tiny ball bearing just bounces off the football. And this is what is called an elastic scattering. So what we see in real life happens at the atomic scale as well. It's also called Rayleigh scattering. But if the X-ray hits an electron instead of hitting the nucleus of this thing, then a couple of things can happen. The electron can absorb some of the energy of the photon. And in that case, you would see that this angle of the X-ray would change. And this single crystal over here was essentially designed to detect those changes in the. And using this apparatus, he essentially showed that, yes, you can observe changes in the energy of the X-ray coming out, interpreting that photons and electrons can exchange energy. And again, emphasizing the particle nature of light. So as you can imagine that there are many different kinds of light and matter interactions that have been demonstrated. We have the phenomena such as the photoelectric effect. We have the Compton effect that I just mentioned to you. And then there are also high energy phenomena. As you know that if you take subatomic particles like electrons and positrons, positrons are particles like electrons, but they have a positive charge as opposed to electrons having a negative charge. So in fact, when electrons and positrons meet each other, they can actually create a photon. And likewise, you can have other such high energy phenomena in which you can observe the reverse as well. So that gets us into an area of high energy physics, which I know absolutely nothing about, so we won't talk about that today. Okay. Any other questions so far? Everything clear? Okay. So as I mentioned to you that the Compton scattering, basically demonstrates the particle nature of light. But what is more interesting is that coming back to the formula that describes the energy of a photon contains a term, velocity of light. And this is a very nice table I found in which you have the earliest estimates of velocity of light to the modern day accepted value. So the first time the velocity of light was estimated was by an astronomer called Olaus Romer. And he was essentially looking at the motion of Jupiter's moons and how they would eclipse with respect to the Earth. And given the they had some idea about the relative position of Earth, Sun, and Jupiter. And based on those motions, you would have expected the eclipse to happen at a certain point. But the eclipse was always observed some 1,000 seconds later, right? So Romer basically estimated that the reason we observe the eclipse 1,000 seconds later is because it takes light that much time to travel from Jupiter to Earth. And based on that, he estimated that the velocity of light was 214,000 kilometers per second. And then, of course, there were other, I haven't gone into all of these measurements, but the Michelson-Morley experiment was the one that was, and Foucault and Michelson both used rotating mirrors to estimate the velocity of light, and they came closest to the current adopted value. You see, they were at 298,000 kilometers per second in 1862. And today's accepted value using the most advanced laser technology is 299,792.458 kilometers per second. So speed of light is constant in vacuum. And today I find this the most remarkable aspect of the properties of light.
Hi, Doreen.
Hi, Chad.
Taking a break from the physics lab?
Yeah, I'm actually thinking of explaining the Planck constant using my cup of coffee.
I'm curious. Try me.
Well, see, in classical mechanics, energy is continuous, meaning if I take my sugar dispenser, I can pour any amount of sugar into my coffee. Any amount of energy is okay. But Max Planck found something very different when he looked deeper. Energy is quantized or discrete, meaning I can only add 1 sugar cube or 2 or 3. Only certain amount of energy is allowed.
Not 2 1/4.
Exactly.
I see.
And same thing when this cup of coffee releases heat, like I draw it in here, the energy is equal to the Planck constant times the frequency of the radiation that carries the heat.
And your team has just measured the Planck constant, right?
Yes, we did indeed. This year we measured at NIST the Planck constant, and we found that H is equal 6.626 10 to minus 34 kilogram per meter square per second.
10 to the minus 34, so that's really small.
It is, and the uncertainty is very small too. It's 0.6022 10 to minus 34 kilogram meter square per second. And if you divide those two numbers, the accuracy of our measurement is 34 parts per billion. For example, to give an analogy, if you measure the distance between Washington, D.C. and New York, which is 230 miles, and I can tell you the distance to within 0.5 inches.
Wow. So now I understand the Planck constant better, thanks to Darina Haladad and her coffee.
So that kind of hopefully helps you understand the Planck's constant better, that it really is a fundamental constant. So I would like to make a point here that very few things in science are that simple, that you arrive at an understanding of an energy that are based on two constant values and the wavelength, which is the variable here. And with this understanding, there's a lot about light that you can manipulate, you can use it to create technologies that benefit the humankind. For example, given now the knowledge of how to describe the energy of light and how light interacts with matter, we can now understand refractive index in a much better way. So refractive index is now no longer an elusive concept. It is essentially the ratio of velocity of light between the two media. So if you are talking about the refractive index of glass with respect to air, then it's the ratio of the velocity of light in glass versus versus the velocity of light in. And in fact, people have also identified substances where light can even travel faster than in vacuum. And these substances are actually called substances with a negative refractive index, because for whatever reason, their light is able to absorb energy from those substances and travel faster. So with this, I'm going to briefly also mention one more property of light, which is called a polarization, which I didn't talk much about. So the direction in which the electrical vectors of the photons oscillate with respect to the propagation of light, that defines the polarization of light. So you can have all vectors oscillating in one direction, then that would be a linear polarized light. Your vectors could also be undergoing a spiral like that as they propagate, and that's called a circularly polarized light. Likewise, you can also have an elliptically polarized light in which the light has some component in y direction and some component in x direction. And the ellipse shape would be depending on how much those components are. The reason I brought this up is because you can use even the polarization of light to do some interesting biology. So what have we used light most for? We have used light to make telescopes because we want to see the stars, we want to understand the mysteries of the universe. We have also used light to make microscope objectives or make microscopes, which allows us to see very, very tiny things inside living organisms or even inside materials. And we use light to take pretty pictures every day. And in all these scenarios, one of the most fundamental feature is that the larger the area from which you collect the light, the much better is the resolution. So as you know, you must have seen photographers at the Olympics sitting on the sidelines with really, really large cameras with very big lenses. And those lenses are really, really big because they want to capture as much as a angle as possible so that they can not only zoom in very close to where the player is playing, but also capture all the expressions of the player. Likewise, the bigger the diameter of the telescope, right, the more distant stars you're able to see. You can see Jupiter rings very, very clearly if you are looking at it from a telescope where the diameter maybe is 3 or 4 meters, as opposed to, let's say, a few inches. And in the end, as you know, that there are big telescopes that have been put in the sky outside of the Earth's orbit. One of them was the Hubble, and more recently is the Hale telescope that has gone and is really giving us a lot of, helping us solve mysteries of nature. But I'm going to show you some examples of what has been done in biological sciences to uncover its mysteries. So the microscopy is essentially mostly using visible wavelength of light. And as you know, that the visible wavelength of light is visible to the human eye, at least, is from 700 nanometers, which is the far red region, to about 400 nanometers, which is the deep violet region. And the size of the object that you can see with these different wavelengths of light also varies based on the wavelength. So with a 700 nanometer light, you can see an object which is 370 nanometers big, while with a 400 nanometers light, you can visualize an object that is about 200 nanometers big. So this basically demonstrates the wavelength dependence of the resolution of an objective. Scattering is one thing that destroys resolution both in astronomy as well as in biology. So in astronomy, when you build a telescope which is on Earth, then it is trying to capture photons that are coming from outer space. And these photons, as they start entering the Earth's atmosphere, they start interacting with the air in the atmosphere. They will start undergoing collision, and the whole light then starts to get diffused. That is one of the major reasons why the Hubble Space Telescope was sent out of space, to get rid of this scattering problem. In biology, any sample is always has structures that are above it and below it, let's say any piece of tissue. And if you try to focus, like if you try to put a microscope over your skin, you can never see your blood vessels. You may see some skin cells, but nothing below it. So that's partly because light cannot penetrate very deep, and whatever light does penetrate, when it comes out, it scatters, so it cannot enter the microscope objective properly. So researchers made efforts to get rid of this scattered light by essentially making sure that light is only collected from the plane in which you focus. And that's called a confocal microscope. So here is one example of light coming from a regular sample and something called a confocal microscope. And you can see that how the images become suddenly very, very sharp. So one of the things in biology is that if you only use light to image biological samples, then you have no information about the actual molecules that are doing the job. So here on the left-hand corner, the video that you're seeing right now is a video using a technique called video enhanced DIC. This uses polarized light, by the way. And what you're seeing is a cell that is dividing. And these long pieces or these long strings are chromosomes. So this cell essentially lines up initially, and the chromosomes start to divide. And then after the chromosomes divide, they segregate into two poles, and those two poles start pulling apart. And this is what is called a phenomenon known as mitosis. And you can see how the cell then undergoes the division by pulling those two pieces apart. You can see the same thing in here in something called phase contrast microscopy. Again, those two, the chromosomes separate, and you can see how the two cells divide into two individual daughter cells. So in both these examples, we are not looking at a specific protein. We are looking at the whole cell and light going through that cell. But in the about a few hundred years ago, researchers were aware of compounds which essentially were called fluorescent. So what does fluorescence mean? So these compounds would essentially absorb light at a particular wavelength, but then emit light at a different wavelength. So here is an example of the energy state of one such fluorescent compound, that it would absorb a photon when the electrons in this molecule are around the S0 state, and then they get, after the absorption of the photon, they would go to the S1 state. They spend some time, lose some energy, and then release that energy in form of light, which is then observed at a higher wavelength. because they lose the energy, the light is emitted at a high wave. This has made a huge advantage because you can actually separate out the excitation light from emitted light using a filter and making molecular imaging really possible. So here is an example of molecular imaging. So here you're seeing a video of an embryo of the fruit fly. Have you seen fruit flies in your house ever? They usually, there's a banana you haven't eaten for a few weeks, it will start attracting fruit flies. So that's why they're called fruit flies. So researchers have done a lot of experiments with those because there's a very convenient model. You can see here that there is a centrosomes lighting up as the cells start to divide in the peripheral region of this embryo. So fluorescence is a nice way of molecularly identifying specific cells, specific proteins, and what they're doing. Here is another example using confocal microscopy of how a process, something known as dorsal closure, takes place in Drosophila. So this is a developing larva, and you can see how it is how it kind of closes in this what is called dorsal patterning in these fly embryos. You can also study wound healing. The same dorsal closure here you see, you can create a hole using a laser beam and watch how that hole fills up back again. And you can study wound healing using such live cell imaging. So this is both are examples of confocal microscopy and molecular imaging. So one of the challenges, as I mentioned, was that confocal and wide field microscopy does not allow you to image deeper than just the very surface. And that surface is literally 50 microns. But what if we wanted to image deeper, let's say up to 1 millimeter deep inside the tissue? So here another technique called 2-photon microscopy was invented. And in this technique, essentially, it took advantage of a very interesting phenomena where you can take 2 low energy photons and be able to have them simultaneously absorb energy. And that would only happen at the focal point of the objective. So here you can see this is single photon imaging. You illuminate the whole tissue, but you only go up to 50 microns deep. But in figure B, you see that it excites also in that same small spot in the center, but because you're using infrared light can penetrate deeper in the tissue, therefore allowing you to image much more deeper. So using such phenomena, such 2-photon microscopy, researchers were able to visualize how T cells and B cells traffic inside the lymph node of a mouse. So on the right-hand side, these red cells are B cells and the green cells are T cells. So they are, as you can see, how they are, nicely crawling like amoeba, and that's called an amoeboid movement of these lymphocytes. So, and this is a live mouse and live T cells. So you can watch an immune response happening in real time. But then the researchers were not satisfied with the resolution that they were getting. If you take a point source and put it on an objective, let's say it's a single molecule, the image of that single molecule is a diffraction limited spot. It looks like a large spot with lots of rings around it. And this is also called a point spread function. And this is the best image that you can get of a spot that is really, really tiny. So, but researchers said, you know what? I'm not going to image all the spots at once, but I'm going to image each spot or each molecule one at a time. And I will generate large number of such images. And rather than using the raw data to construct the image, I'm going to find the center of the point spread function. So while the entire image was useless, the center of the image was determined with great precision. And using this kind of technique, they were able to generate much clearer pictures of a cell. So this is a cell, that's the nucleus, and here you see different subcellular structures, including microtubules and endoplasmic reticulum. So this is the power of these new techniques called super resolution imaging. And then I did mention that, or rather, I didn't mention, one of the problems with microscopes that have been built so far is that while their XY resolution can be enhanced dramatically, the resolution in the third dimension, which is the Z dimension, is really, really bad. So it is twice as bad versus the XY. So to solve this problem, they came up with another technique called light sheet microscopy. So here you basically take two objectives. With one objective, you create a sheet of light in the sample, and with the second objective, you detect it. So in the end, you're always imaging in XY. You're never imaging in the Z, and therefore you can come up with really beautiful images. Here you see that this is a single cell, and these spikes that you see are the individual filipodia of the cells that have never been visualized before. And you can see this in very, very high resolution. So this light sheet microscopy has really led to a revolution in microscopy. And here on the left is another example of you're actually visualizing a single bacterium, another protein, which is doing some it's called a scramblase. It's an enzyme. And you can see how it creates motion in this bacteria. And earlier imaging at this scale on a bacteria was just not possible. And the movie I showed you before of the dorsal closure in larva, if you now visualize the same phenomena in using light sheet microscopy, you can see you can observe far greater detail with which this closure of the dorsal region of the embryo takes place during development. So lastly, I want to show you how do you beat the resolution in time. So this is something called a femto camera. And what it is allows you to visualize a single pulse of light travel through a Coca-Cola bottle. So the trick is that they are not imaging the same pulse of light. So there are multiple pulses of lights that are continuously going, but they are able to measure the time difference between one pulse of light and when the camera is activated. And they keep on changing that delay. And based on that, they are able to construct the entire motion of light through the Coca-Cola bottle. If it was a single bullet, for example, then that's it. You would not be able to do the experiment again. But because it is light, you can just keep sending different pulses of light. I'm open to questions.
Thank you so much for that cool presentation. Anjali and Nandana, do you want to start our Q&A?
So to start off the Q&A session, we'd like to ask Dr. Varma a few questions. If anyone has any that they'd like to ask now, you can put it in the chat box, or you can raise your hand and ask it yourself. I'll start off with a question. Dr. Varma, what was your major in college, and how did that affect your journey and your interests going forward?
My major in college were physics, maths, and chemistry. My father was a physicist, so that's why I was very much inspired by physics. But as I mentioned, as Anu mentioned, I was very much inspired by my high school biology teacher. And so when I finished my college and master's in physics, I got an opportunity to do my PhD in cell biology. And I took it because I liked the whole idea of blending physics and biology.
You mentioned Planck's law. What are the applications of Planck's law in modern science and technology?
Well, Planck's law essentially gave rise to understanding that energy of electrons and energy of photons is quantized. So it gave rise to the invention of lasers, gave rise to lasers, communications, even we go to get an MRI scan. That is also a quantum phenomenon. Or we take X-rays. Almost everything that we do today can be traced back to Planck's law. So because it gave us a fundamental understanding of how light and matter interact. So it has implications on how iPhones are made, how computers are made, how computers function, everything. So it was a very fundamental discovery. And think about it, that the Planck's constant was not derived from some theory. It was a number that fit a statistical distribution of photons. So it was something that any high school student could have done.
Okay, so thank you. We have a question in the chat. Gowrie asks, out of all your knowledge in the STEM field, chemistry, physics, and other categories, what is your favorite?
My favorite, actually, I don't make a distinction between these different subjects. I call them natural sciences. In my work today, where we are trying to develop therapies for cancer and autoimmune diseases, we use physics, we use chemistry, we use biology, we use mathematics. So going forward, I would advise all of you to not think of these as separate subjects. You will do the most exciting and the most creative work if you think about that you're studying science, and the objective of science is to understand nature.
Thank you. Oncology is a field where a lot of information is unknown or yet to be discovered. How do you approach the development of therapies for cancer when faced with that obstacle?
That's a great question. And I think we do it collectively. We do it by experimentation. We do it by learning from each other's mistakes. So there is a very nice movie. It's not a movie. It's a documentary on Amazon Prime called "Cancer: The Emperor of All Maladies." It was based on a book written by Siddharth Mukherjee, and in this documentary, which is about 6 hours long, it traces the history of cancer treatment and the war on cancer. So it's all started with when they observed the emergence of childhood leukemias. So in the 1950s and 60s, when children would get diagnosed with leukemia, there was absolutely no treatment for them. They would very, very sadly end up dying without any treatment. And at that time, if you were diagnosed with cancer, it was 100% that you would die. nobody lived for more than 5 years after the diagnosis of cancer. Today, almost more than 60% of the cancers have treatments which allow 99% of the people to live beyond 5 after diagnosis. And so advances in cancer therapy over the last 60 years have been slow and incremental, but have been additive. And now the situation is such that our life expectancy has gone up to 80 years from 54 years, partly because of these incremental improvements. So that's what I keep my hopes open, that we continue to make progress by asking new questions, finding answers, developing therapies to test safely in humans, and then keep repeating that process. Anu, you have a question, and then I can address the question in the chat.
Yeah, you were talking about how light is in particles. How come it still has a wavelength?
You can call it a particle which has a packet of wave in it. That's the simplest way to describe a photon. And I think that was in my second slide or so, where I showed kind of a wave of two different wavelengths. So those are basically what the best way to describe a photon.
Thank you.
So Isaac has a question. So what is the most interesting thing that I have discovered myself? I have made two discoveries, one during my PhD and one during my postdoc. During PhD, I used polarized light to measure distances between two proteins. And using polarized light microscopy, I showed that these proteins were clustered. And this was something that was not known before. And then when I was a postdoc, I basically described how the T cells in our body also form, when they are mounting an immune response, receptors on the surface of the T cells will undergo very tiny scale clusters. And I had used a microscopy technique that I didn't have a chance to tell you about, called total internal reflection fluorescence microscopy, that allows you to image only the plasma membrane of any given cell. So those are the two things that I'm most proud about.
Okay, so the next question. As the director of oncology at AstraZeneca, what kind of management work do you do in addition to your scientific ventures?
I think one of the things that we have to make sure is that the team that works for me, that their goals and objectives are met, right? And that their goals and objectives are obviously scientific, but they also have to align with the company's mission of developing new therapies. So my management work is usually centered around providing focus to my team members and make sure that the team members are producing data and making discoveries which will allow the company to make medicines.
Thank you. Have you previously used magnetic nanoparticles in your research with immunotherapies, and what would you say the importance of them is?
So I have not used them personally, but there is one very interesting application of magnetic nanoparticles that Google was trying out an experiment. So Google came up with this idea that you could make magnetic nanoparticles that had antibodies on them, which would detect very small amount of proteins that would be secreted if you, let's say, have some infection or you have some disease. So their idea was that we would let these nanoparticles circulate in your body for 2 or 3 days, and then we would wear a magnet and collect them and then reanalyze them. Yeah. So I don't know what happened to that project. I never saw any output from it, but at least that was one concept of how magnetic nanoparticles could be used for early detection of cancer, for example.
Thank you. We have another question too. So throughout your presentation, you mentioned many different experiments and theories from prominent scientists like Einstein and Compton. Which one do you believe was the most revolutionary or influential on the work that you do today?
The work that I do today. Wow. It will be very difficult for me to pinpoint one scientist because my work is so applied, and any technique that we develop in microscopy is a result of work done by hundreds of different scientists. And there are things that we assume to be true because it has been shown as a result of work done by people throughout 60, 70 years. So it's very difficult for me to pinpoint one. It will be very unfair of me to pinpoint that there's one scientist who has influenced me the most.
Thank you. What was your experience like at NYU?
NYU had a great time. It was in New York City, so it was never boring. I loved working there. I was there for 5.5 years. Anytime my experiment would stop, I could just walk out and experience the city, find good food. It was a great time. I recommend that everyone on the call spends at least 2 years of their life in New York City.
Thank you. So you mentioned, right, the director of oncology at AstraZeneca. So what does the day look like to you when you go to office or when you start work in the morning? What kind of activities or meetings do you join on a day-to-day basis?
So I have 3 kinds of meetings. Most of my meetings are with my team members. I meet with each one of them every week so that they can ask me questions and I can guide them for further experiments. I review their data. I help them out when experiments are not working and so on and so forth. Then second kind of meetings I have are meetings with my colleagues that are either at the same level as I am or who are superior to me, which are more sort of trying to understand the overall direction of a particular project. Some projects are short-term, some projects are long-term. And then the third kind of meetings are departmental meetings. There are meetings in which more than 10 people are involved. And then I spend a lot of time reading and also writing proposals. Reading should never stop. And yeah, that's what my day looks like.
Sounds cool. Thank you. What are different types of objective lenses used in light microscopy, and how do they affect magnification and resolution?
So there are the only parameter of an objective that affects its resolution is called the numerical aperture. And the numerical aperture is essentially the cone of light that is generated if you hit the bottom of the objective with a parallel beam of light. And if you measure the angle of that cone, the larger the angle, the greater is the numerical aperture. Yeah. And the greater is the resolution. And the same holds true for a camera lens too. The camera lens has the same concept of a numerical aperture. It's just that the numerical apertures in microscope objectives are far greater than in camera lenses. So the numerical aperture essentially is what dictates the resolution. Magnification has very little consequence. because you can have a low magnification, high numerical aperture objective, which will do better than a high magnification, low numerical aperture objective. So that's about the concept of numerical aperture. Certain objectives are made of different materials. So for example, there are some dyes that emit light in the ultraviolet. So you need to make objectives that can detect that. Certain objectives are made to do turf microscopy. They have even bigger numerical apertures, but then they start to have spherical aberration a little bit if you go higher than that. So yeah, the catalog of objectives is huge. I can go on and on, but if anybody wants to reach out to me later, I'm happy to explain.
Would you say there have been any recent advancements in your research with cancer or diseases in general?
Yeah, I think that one of the most recent advances that have happened in cancer is trying to understand why cancer happens. And earlier it was thought that cancer is a disease that happens because of mutations that accumulate. But now the emerging consensus is that you can get cancer also without any mutations. So the whole idea is that there is a breakdown of tissue level homeostasis, as they like to call it. And if I can explain that better, is that in any tissue of your body, there are basically different cell types that are communicating with each other and supporting each other's health. Okay. What happens that most of the time, that communication between those two cell types starts to break down as we grow older. And very often, when that communication breaks down completely, you start getting cancer. So the focus of cancer research has now slowly shifted more towards understanding how we age. And it has become a problem of aging rather than a problem of an insult like smoking, right? So even today, the single most cause of cancer is smoking. It's like gives you a 20% chance of getting cancer if you smoke.
All right, so this seems to be the end of the webinar. So first, I would like to thank Dr. Varma for joining us today to talk about light and fluoroscopy. Thank you so much for taking your time to teach us about this subject. I would also like to thank all of you for joining us today in the webinar. I hope you guys enjoyed it. So be sure to look at kcsmw.org/youth so you can see our future events. And I hope you guys have a good day.